extreme control be here. And everybody will see that there have the 4 types points. The A, B, C, D, I give some description. Like the point A, everybody will find that when the dx dt at this time increased and the dy dt also will increase, then we want to keep the point A also increased. And like this point B, when the dx dt increased, but at this point the dy dt decreased, then we will change the direction. So we need the dx dt equal to the negative k. So we have this things. This is just some introduction about the extreme second control. Very basically, and based on these things. And we show some popular the extreme second control for the integer order versions. The first one is the sign extreme second control, and this extreme second control just based on the perturbation and average method. And the second one is based on the sliding model method, and we call it the sliding model extreme second control. And for this sliding extreme second control, we have the time switch function be here. And according to this time switch function, there exists a series of the sliding surface. Based on the sliding surface, we can need the y achieved to the y star and always stay in this point. And all of these things we can find in the Dr. Zhang's book, the Extreme Second Control book. I have cited this book in my reference.
Okay, I want to add a comment. We have Dr. Chun here.
Okay.
And he wrote a book on extreme second control.
Yeah,
we refer to this book a lot.
Yeah. And also, in this book, they will give us some introduction about the other the extreme second control, like the numerical network extreme second control, or the other 2 extreme second control. And in this presentation, I will compare the sign extreme second control and sliding model extreme second control and the numerical network extreme second control, and apply this 3 class controller to the energy systems and compare the which one is the better one, and except the integer order extreme second control, I want to extend the integer order extreme second control to the fractional order extreme second control. Why? Just because everybody will know, statically will know that extending the derivative or integral from the integer order to the fractional order have a firm and the non-standing foundation. So if we add the fractional order controller to the integer order systems, maybe we will find a better flexibility to have a better performance. So I said this from Dr. Chun's paper. Now, for the control systems, there are the 4 types. The first and the second types is for the integer order plant, the systems. So most of people add the integer order controller to the integer order systems. And now, when we extend the integer order controller to the extended controller, maybe we will find the better conformance just because we have the more options. So in this presentation, I focus on the fractional order control to the integer order systems. and based on the integer order sign function, based on the sign extreme seeking controls, and our other group members have extended and compared the integer order sign extreme seeking control, and this student have changed the integer order integral to the fractional order integral, and they also apply the fractional order sign extreme seeking control to the photovoltaic systems, and have published the paper in the 2012 the CDC conference. I also said I will set this conference paper to everyone. And the other things is based on the integer order sliding model extreme seeking control, and we designed the fractional order sliding model extreme seeking control, and the difference between the integer order and the fractional order extreme seeking control is this part. And I changed this part. Change the integral to the fractional order integral. And based on this part, I get the better performance, like the faster convergence speed and the higher accuracy. Later, I will show the experiment result for the lighting system and the photovoltaic systems. And now I will show some system descriptions. First, I give everybody the introduction about the photovoltaic systems, and just because everybody now should to know that the energy saving is very important for the world. Just because we need to have the human cistern, so the solar energy is a key opportunity for the increase in the role of the renewable energy in the electronic grid, but we want have the higher efficiency to transfer the solar energy to the electronic city. So we want to keep the energy, the power output always at the maximum power point. And now, so many people have applied the extreme seeking control to the as the maximum power point. Want make the output power always keep the maximum efficiency. And now this figure shows that when the different temperature or the different irradiation, the power and the voltage curve, or the power or the current and the voltage curve will be changed. So we want to apply the extreme seeking control. We want to use the maximum power point tracking, always find the optimal point. Like this point in this solution, we want to find this point because this is the maximum power point. But this point always changes, and just because that the temperature or the other environment condition changes. So we want. This is the reason why we want to use the ESC be here, just because the ESC and one advantage of the ESC is that it can independent on the systems, and so it means that when the systems is changed, but we can use this controller to always find the changes optimal point. And in order to show the in order to show the comparison of the, for the photovoltaic systems, in order to show the comparison of the different ESC systems, so I use the simple model from the Go and the many papers. And in these models, there is a simple relationship will be here. And they also provide a very simple M function can be used. And in this simple model, the maximum power point should be the 48 watts be here. So now I will show the other energy systems, the lighting systems. And actually the lighting systems, and in order to save the light energy, because everybody will know that the light illumination will cost a huge electricity. So everybody will think that maybe we can save the energy. We can combine the, because now we use the artificial illumination, right? But if we can get some like the natural lights, maybe come from the sun or the other room's lights, we can reduce or maybe reduce some of the artificial lights. Then we can reduce some of the cost, can reduce some the lighting energy. So we build the small office. We call it the miniature office, and we have the two groups. The two light group will be here. This is the red lights, and it's because in this lights, I show a picture for it. Yeah, this is the inside. This picture, this is the inside of this small box, and we will say that this is the real light. Here, this light is there is a light sensor, and this red light is near the light sensor, and the yellow light is far away the light sensor. So now our purpose is that sometimes, when we stay in this room, maybe we want read a book, or sometimes we want sleep or something. So our demand of the lights is different. But when we set some set point, we want all of these lights can achieve to our demand. So we need all the four lights can give us the right illumination. But if like this way, if we want the illumination is 500. So we can ask the red lights, the group, give us the 300 illumination, and the yellow light group give us the 200 illumination. It can satisfy our, our requirements. Or maybe we will ask the yellow light give the 215, or the red light give us the 215. But it also can satisfies our requirement, right? But the different options, both of the two options can achieve to our requirements. But the different, because for the red light, the different, how can I say?
Energy.
Yeah, the different. Yeah, but the two options, there are the two the energy consumptions. So which consumption is the smaller one? We don't know. But if we find the smaller one, we always use the smaller energy consumption, right? Because we can save the money. So this is why we build this office, the lighting box, and want to do these things. So at first,
you don't have time.
I don't have time. Because I think this is the important thing for my presentation. So.
Okay, go ahead. Give you 3 minutes.
Okay. So, our
It's running?
I think so.
Great. So this is a hardware in a loop simulation system. So the real system is linked with the computer through MATLAB Simulink through the Arduino interface. It's a low-cost solution. With 200 Hz bandwidth, so it's enough for.
So the now everybody says. I'm sorry, just because. Yeah, and the.
It's Arduino part.
Yeah, the.
So if you change your.
So this is just for the illumination, and when we say the illumination is the 650, the purpose line is the real illumination in this room, and the data get from the night sensor. And I also want to show the other things.
So you have multiple light bulbs. What's the best combination so that the
Yeah, and
it's online?
this is the energy. This is the energy, and the yellow line is the total energy. I mean, the two groups that consume, and the blue one is the red light consumes the energy, and the purple line is the yellow line. Yellow light consumes the energy, and I need the because there is a relationship between the two groups, and I need I represent the current of the total current, and the total current is split in two parts. The one part I denote I1 give to the reader nights, and the second group, the second current I2 give the yellow group, and we have the relationship like this, and this is our energy. And I mean, for this experiment, when I switch the omega, because I give the sign to the omega, so the omega can change from the 0 to 1. We will find that when we always can achieve to our illumination requirement, but the energy can be changed. Everyone can see the green or the yellow line. This is the total energy. Every people will find that there has some point can make the energy always is the small. Now we can find the smaller energy. The small is the energy. So when we find it, we apply our because we not only want to find just want to find the small energy. We always want to find we want to keep the energy always at the minimal energy output. So we apply our controller B here, and we see the result.
So what is it?
Now,
Is it controlling now?
this is not control signal. This is the energy when we apply the control. Because the first one is we didn't apply the control here. We just give the sine function be here. Let the omega, let here omega changed from the 0 to the 1. And
The yellow one is the total energy?
the yellow one is the total energy. So it can automatically to find that the minimal energy be here. And yeah, this is very sensitive. Because you see, when we drop these things and the energy is go up, and and this is down. It's very sensitive. So I just show some results, and I put the presentation. So this is the curve. Oh, what happened? Oh, this is the curve. I mean that when I here the blue this is the blue line. The blue line is my set point. I mean that now this is our requirement. What illumination we need, and the green line is the sensor. We get the real illumination. It can show that when we use our controller, we can need the real illumination achieved to our requirement. But when we achieve to this purpose, we switch the omega from the 0 to 1. It means that we will find the total energy will be changed. We also will find that everybody say the real point. This is the minimal energy point. So it means that when we achieve to this purpose, we also want to keep the energy consumption in this point, because in this point we can save a lot of money. So we apply our controller here. For this part, we can change it to the sign extremity control or the sliding mode extremity control for the integer or the version or the fractional or the version to this part, and I get some results. This is for the sign extremity control. When I apply the sign extremity control to the lighting systems, we will find that just because there is a disadvantage of the sign extremity control is that we need put the this is very sensitive, and when we apply here, this is a comparison of the fractional order extremity control and the integer order extremity control. We will find that the blue line is under the fractional order extremity control is more faster and more accurate than the integer order extremity control. The reason is because we in the controller we replace the integer order integral with the fractional order integral, and the exact explanation, and we have shown our papers. I didn't have show these things to here. And this is another, just because maybe maybe someone will say that this is just a specification for the fractional order things that things. So I show the more experimental resultation here. And the green and the blue are on the that's here. Yeah.
Okay.
Oh.
You already explained.
Oh, I'm sorry. And no conclusion. Just the conclusion is that.
What's the take-home message for people not expert in control?
And I didn't understand show that.
Take-home message means what?
Take-home the message is, I think, here.
You can achieve the same illumination while maintain at the minimum energy consumption.
Yeah, I think the conclusion should be use the fractional order controller. You can save the more money.
That's a better take home. We should write down. Excellent. Okay, good. Thank you. Yeah, actually, this hardware in the loop simulation is a kind of very good classroom to apply. So, Professor, you have a question?
So you have a number, to some extent you can say.
Yeah. So, Professor, do you want to can you finish in 10 minutes? We're really running out.